to stay on schedule. So hello everyone, I'm Mihaela. I'm a research engineer at DeepMind and one of the organizers of this tutorial. And today I'll talk to you a bit about VAEs and GANs, and specifically how to merge VAEs and GANs, and what does this merger promises and what it actually delivers. And I feel like this talk has been very well set up by the previous speakers that have talked about maximum likelihood learning, and Emily talked about using adversarial losses in feature space, and so on. So GANs have really pushed forward the state of the art in image generation. We see that now we're able to produce better and better images on ImageNet, like Ian showed earlier. But if you've trained a GAN, or if you follow the literature, you've seen that they're somewhat unstable to train and sensitive to hyperparameters and its initialization. So if you train a GAN on a data set of faces, like Celeb, for example, and you haven't tuned your hyperparameters, you might see something like this. This is what was mentioned earlier as mode collapse. Instead of the generator being able to capture the diversity of the data distribution, it collapses into generating the same image again and again, or a few images again and again. And this is a problem, and a lot of the efforts in the field have focused on solving this problem, either by looking at architectural choices, like Ian showed in his first talk, or by looking at the dynamics of the adversarial game and changing the loss function, like, for example, looking at Wasserstein-GAN losses, or by trying to merge GANs with some types of models that don't have this problem. And this was mentioned earlier in this idea of encoder-decoder GANs, or VAE-GAN hybrids, as I will call them. And why does it make sense to merge these two approaches? Why does it make sense to look at VAEs and GANs and kind of merge them together? Well, firstly, it makes sense to look at merging GANs with maximum likelihood, because maximum likelihood does not collapse. Specifically, when you train a model to maximize the likelihood of the data, in the model objective, you have this expectation over the empirical data distribution. You have this expectation over your data set. So the aim of the model is to try to explain the entire data. So because of that, because of this explicit expectation, maximum likelihood models don't collapse. On the contrary, they have this other problem that was shown earlier of trying to explain points in between data to be able to explain the entire data set. So this looks a reasonable approach, but maximum likelihood gets a bit more complicated when we're thinking of latent variable models. So why would we want to do latent variable models in this case? Well, firstly, if we want to do maximum likelihood in the setting of GANs, or merging maximum likelihood with GANs, we know that GANs are latent variable models. This means they take some noise from this unstructured distribution, they pass it through the generator, and they generate images in the data. But there's another reason why we want to use latent variable models. We want to leverage the underlying data generation process. So if we think specifically about images, they're very high dimensional. And only a small set of all possible pixel permutations are actually images that we care about. For example, images of faces. And we can imagine that we can embed all the information in the set of images of faces into a lower dimensional space. So for example, if I have one latent variable that says, well, the color of the hair will be blonde, that will represent multiple pixels in image space. That will entail that the color of the hair will be blonde. So this is why we want to do latent variable modeling. But in maximum likelihood, latent variable modeling entails an intractable integral. Because now when we're trying to compute how likely a particular data point is, and remember, we have to do that because that's the goal of maximum likelihood, to increase the likelihood of data points. Now you have to integrate over all possible latents. So you have to integrate over this prior distribution over latents that you choose. So often we choose a Gaussian distribution, for example, to be able to explain that particular data point. And not only is this integral intractable, it's also very expensive to approximate using something like Monte Carlo. And why is that? Why is approximating this integral expensive? Well, it is because the prior P of Z doesn't know anything about the data point X that you're trying to measure the likelihood of. We can make this sampling more efficient if instead of sampling from P of Z, which doesn't know anything about our X, for example, in this case, if we want to find the likelihood of this particular face, and if we sample from all the possible spaces of the prior, that sampling is going to be very inefficient. But if instead we focus the sampling, instead of sampling from P of Z, sampling from a distribution that knows X, sampling from a distribution Q of Z given X that has the face as an input, we can make the sampling more efficient because we can find that part of the latent space that can explain the input that we're interested in. So we can replace P of Z with Q of Z given X such that this distribution that now is conditional takes the input that we're interested in as a condition, and we want to stay close to the prior because when we sample, we will still sample from the prior because we don't know what input we want to see in the end. And this is the key terminology and the key concepts behind variational autoencoders, or VAEs. So VAEs integrate this approach of making, let's say, the sampling more efficient with deep learning. So how do they do that? Well, we now have these distributions, Q of Z given X. Remember that now this is a conditional distribution. It takes the input X. And a generator that's now conditioned on the latent distribution. And these two distributions are parameterized by some moments, for example. So if we choose Q and P to be Gaussian distributions, we want to find the mean of Q of Z given X, for example, and the variance of Q of Z given X. So what we do is we pass X through a neural network, and this neural network has two outputs, which are the mean and the variance. And then using some tricks, we can train this with backpropagation to learn the moments of these two distributions. So now we are using deep learning to learn distributions such that these two distributions, Q and P, can explain the data. So the aim specifically of these variational autoencoder is that Q can explain X. So remember that we started with making sampling more efficient while staying close to the prior P of Z. And this is done using the variational lower bound that's shown here, kind of split into two, which aims to make sure that Q and P together can reconstruct the data. So this is a reconstruction loss. Based on different choices of P, you either end up with an L1 or an L2 loss and so on, while Q stays close to the prior. So this is a standard KL divergence that measures, let's say, distance between distributions. And an important thing to note about variational autoencoders that is different than GANs is that they don't have any cost on samples. So with GANs, you create a sample, you pass it through the discriminator, and you evaluate samples during training. For variational autoencoders, we don't have that. What we have is that the model learns how to reconstruct using the reconstruction loss, and it learns how to bring samples close to reconstructions by matching these distributions in latent space, right? Remember that now we have this Q of Z given X, which is a conditional distribution that needs to be matched to the prior. So the approach to sampling that VAEs take is very different than the ones that GANs take. And the nice thing about VAEs, apart from the fact that they allow us to do maximum likelihood training using latent variable models, is that you can now learn distributions over representations. So if you train a standard autoencoder, you will not have any control over the kind of distributions that the codes will have. But if you use these variational autoencoders, you can now firstly quantify uncertainty. You have this distribution over codes in latent space, and you can say, well, this particular image, there's a big variance in latent space. But it also allows you, using the KL term, to impose prior structure over learned representations. So for example, one of the types of prior structure that we will want to have is disentangled representations. So Emily talked about this in the context of pose. and content. But here, we talk about it in the sense of we want different dimensions in latent space to encode different semantic information. So for example, if I'm a reinforcement learning agent in a room and I'm learning representations of the world around me, I would like that one latent dimension encodes the room that I'm in, the second latent dimension encodes the color of the objects that I'm seeing, and so on, rather than having all mangled in one code. And it has been shown that learning this kind of representation actually helps with generalization. You can take a reinforcement learning agent on one task and generalize better in another if your representations aren't so mangled with each other. So far, VAEs sound great. We can do maximum likelihood learning with latent variables. We can do inference. But if we look at samples, in practice, we see that the samples are often quite blurry, and they don't manage to capture the subtleties of the data. So we see that VAEs fail to match the data distribution and the model distribution, because this is the aim of generative models. But we can also look in latent space. So we've seen that for VAEs to be able to sample, to be able to generate competing samples and to capture the data distribution, they rely on this scale term in latent space. And in a recent paper, we showed that you can exploit the failure that VAEs have to match distributions in latent space to generate really bad samples. So using this approach, we showed that actually VAEs fail to match distribution not only in visible space by generating bad samples, but only in latent space, also in latent space. So a natural question then is to ask, well, what causes this failure? How can we improve VAEs? Well, one of the things that VAEs do is they rely on conditional distributions. So to match marginal distributions, to match the data distribution and the model distribution, they rely on Q of Z given X, so distribution condition on the data, and P of X given Z, a distribution condition on the latents. So this is one thing. Another thing is that these distributions need to be explicit. So you have to choose a model family for these distributions. You have to say Q is a normal distribution and P is a normal distribution, for example. But we know, especially for computer vision, that choosing P to be a Gaussian distribution, and this leads to a L2 reconstruction loss, doesn't capture meaningful similarity in between images. So this is a problem. And this is actually exactly why, one of the reasons why GANs work so well. Because GANs use implicit distributions, so you don't have to choose a model family. You just pass some input to the generator and it will generate samples. And they also don't rely on conditional distribution matching. They only use marginal distributions. So we've started by motivating maximum likelihood learning in VAEs from the perspective of improving mode collapse in GANs, and now we've ended up to a point where we say, well, perhaps GANs can help VAEs as well. So it seems like merging VAEs and GANs would be a very promising approach. So let's see what combining these two approaches promises. So concretely, it promises to improve VAE sample quality and improve representation learning for VAEs. And it promises to increase stability and diversity of GANs, because VAEs are actually quite robust to hyperparameters. You can throw almost anything at them and it will pretty much work. And these are some really big promises. So there's been a lot of people trying to come up with VAE-GAN hybrids to improve both GANs and VAEs. Adversarial autoencoders, adversarial variational base, VE-GAN, Ali bi-GAN, alpha-GAN, and so on. And I'm not going to go into the details of all of these, but I just want to mention in one slide the principle that most of them rely on. And this is the density ratio trick, which says that every time you have a ratio between two distributions, you can estimate that ratio without knowing the closed form of the two distributions. Because, for example, for GANs, we don't know P theta of X. We can only sample from it. And this trick says if you can train a discriminator, so the standard GAN discriminator that distinguishes between these two distributions perfectly, and note this is a keyword, perfectly, then you're able to replace that density ratio with the probabilities that the classifier gives you. So if the classifier says, okay, this is likely to be a sample from the first distribution with 0.3 and 0.7 from the other distribution, then you can approximate the ratio. Of course, often we don't know how to train classifiers to optimality, and especially in the GAN setting where you also learn one of the two distributions for the ratio as well. And we'll see a bit later on how that becomes a problem. Now, let's empirically assess these promises. So the first promise is VAE-GAN hybrids should improve inference quality of VAEs, so should improve representation learning for VAEs. So first model to look at here are adversarial autoencoders that Emily just briefly touched upon earlier. So adversarial autoencoders do one thing. They replace the conditional distribution matching of VAEs in latent space. So now you no longer have this closed form KL with marginal KL that is estimated using a GAN. So this means that now the encoder no longer needs to be explicit either. So you've solved two problems in one go. And we said, well, okay, this sounds very good. Let's see how this compares to VAEs in practice. So one of the crucial properties of VAEs is that they optimize a bound on the log likelihood. So because we have replaced P of Z with Q of Z given X, we actually don't do exact maximum likelihood, but we optimize a bound on it. And however, we see that while we train VAEs, what we expect happens. The bound needs to go up as training proceeds. That means that the model gets better and better at explaining the data. And this is what we want. But if we look at what happens with adversarial autoencoders, we see that the bound does not go up. And actually, this is an effect of adversarial training. And specifically, to be able to use the density ratio trick, we rely on classifier probabilities. And in our paper, we've shown that actually, even if you train the discriminator to optimality, so not using alternating gradient descent, classifier probabilities can be used for learning, and we know that because GANs work, but not for estimation. So that means that VAE-GAN hybrids, and this applies not only to adversarial autoencoder, but to all of them, cannot be compared with other maximum likelihood models. So while VAEs have this evaluation metric that comes out of the box, with GANs you cannot do this, and you cannot do it with VAE-GAN hybrids either. Now let's look at the effect of adversarial training on learned representations. So VAEs have this nice property that they learn sparse representations. What does this mean? Well, often when you train a VAE on something like CVPR18, you use 100 latents. What happens if you use 10,000? Well, what the VAE does, and what you can show here on your left, is that the VAE only uses a few latents to reconstruct the data. So these are the points in dark color. And for the rest, it just sets their distribution to match the prior, because it doesn't want to pay the scale cost of not matching the prior. And what this entails is that, and now if we look on the right, is that most latent representations have mean around 0, because the prior has mean 0. But this is not the case for adversarial autoencoders, because we have replaced this conditional KL. Now adversarial autoencoders, and you can see them here shown in blue, they learn dense representations. So they don't automatically learn to turn off units like VAEs do. That's not necessarily bad, but it's worth having in mind that when you choose one versus the other, you learn different types of representations. There is an effect of this though, is that when you change the number of latents for a VAE to 10,000, these are samples obtained using 10,000 latents, the VAE suffers almost no hit. So these are almost as good as the same samples obtained using 100 latents and not changing any architectural choices, any learning rate, anything, just setting the number of latents to 10,000. Now this doesn't happen for adversarial autoencoders. Even when I change the discriminator, the latent space discriminator, and made it bigger, we see that the samples cannot capture the diversity of the background, for example. They have collapsed and all the background is white. And I'm not saying that adversarial autoencoders don't scale and wouldn't be able to produce better samples in this context. It's just that it requires more tuning, because apart from an encoder and a decoder, like you have with VAEs. Now you also have this code discriminator that needs its own learning rate, and we know that GANs are a bit unstable, so it's kind of propagating in the whole system. Now the second question is, do these hybrids improve generation? And not only quality, but also, remember, stability and decreasing the chance of mode collapse. So to do this, for the purposes of this analysis, we introduce this variational GAN hybrid, which we simply call VGH, that does marginal distribution matching and uses marginal distribution matching and implicit distributions in visible space as well. Because we know this is what allows GANs to produce really good samples. And as another comparison, we look at one hybrid model, a very neat idea of VE-GAN, which instead of matching latent distributions and data distributions separately, it matches joint distributions, and that by matching joint distribution, you also match the marginals. So let's look at the empirical results. Firstly, because we're interested in assessing also stability, so not only cherry picking the best results, we don't only report the best results in black points, but also hyperparameter spread. So the boxes here show how sensitive to hyperparameters a model is. The bigger the box, the more sensitive the model is. And the first thing that we see here, and in this image, higher is better. We see that VAEs and adversarial autoencoders cannot compete in terms of inception score to models that do marginal distribution matching in visible space. So adding that, either using a joint hybrid or by just using standard GANs, takes you a long way in terms of generation quality. Another thing that we see is that our GAN baselines actually do quite well. So our GANs baselines are DC-GAN and Wasserstein-GAN GP, and we see that the hybrids actually don't improve on these baselines and don't improve hyperparameter sensitivity either. So for this particular task, DC-GAN performs best. And it has a lot less hyperparameters to tune. Now, if we look at another metric, which has been shown in a recent iClear paper to correlate with human evaluation, we see the same story. A lot of hyperparameter sensitivity for a lot of these hybrids, including VE-GAN, adversarial autoencoders, and so on, while Wasserstein-GAN GP does quite well here, and again, less hyperparameters to tune. Now let's look at a final metric which directly assesses mode collapse. So this metric uses MSSSIM to measure similarity between samples. And here we don't want higher is better, but we want to compare with the test set diversity because we don't want to be more diverse than the test set. And here the same story repeats. We see a high sensitivity to hyperparameters for a lot of the VAE-GAN hybrids. And we see that Wasserstein-GAN GP actually does quite well. But let's look at samples themselves. So one of the claims was that these hybrids will improve VAE sample quality, and they do. So the VAE samples are on the left, and we see some VAE-GAN samples on the right. They're crisper, they have more details, and so on. But if we compare VAEs with VAE-GAN hybrids, and we say, well, hybrids improve sample quality, well, it's fair to also look at GANs, because GANs also improve sample quality over VAEs. And if we compare GANs with some VAE-GAN hybrids over sample quality, I personally can't see much of a difference. And this is what we've seen also with the metrics as well. So I think this allows us to conclude that at present, so with the current methods and with the current proposed algorithms, these VAE-GAN hybrids do not improve distribution matching either in latent and visible space. Now, one of the things that you might say now, if you're a bit familiar with the field, is, well, how about CycleGAN? Because CycleGAN has been a great success in this image-to-image translation setup. And it looks somewhat similar to some of these models. So you have an autoencoder going horse to zebra, zebra to horse. You have two discriminators, and so on. But what I've talked about does not apply to CycleGAN for multiple reasons. So firstly, as was mentioned earlier, CycleGAN focus a lot on style transfer. Doing style transfer is easier than creating structure, which what we're asking for these VAE-GAN hybrids. We're asking them to generate images. It's also a more constrained problem, and crucially, it's easier to do architecture search because you don't work with these latent spaces for which we don't really know what the wisdom is. So as Ian mentioned in the first talk, a lot of the successes of GANs have come up from architectural changes. But these architectural changes are done on images, and not all of them translate to architectural changes in joint discriminators or co-discriminators and so on. So it's purely a technicality, but we see that this hits these VAE-GAN hybrids. So to conclude, I'd like to say that VAE-GAN hybrids don't seem to deliver on their promise to stabilize GANs or improve VAEs. And what to use is basically dependent on your use case. Do you want good samples? Then use GANs. We've seen today some really good ImageNet samples using standard GANs that have only 2 networks to train. If you care about representation learning, perhaps it's better today to use VAEs. Thank you. We have time for questions? If there are any questions, well, I think we have 1 or 2 questions. Is the next speaker ready?
If there's no question, we can thank our speaker again. Next, I'm pleased to introduce Mingyu Liu, a research scientist at NVIDIA. While his work has been known for many things, his recent line of work on image translation has been state-of-the-art in many tests, including paired translation and then also unpaired translation. I'm very pleased to introduce Mingyu.
Thanks for the introduction. So let me find this one. Maybe some video playing problem. Thank you. This is Mingyu from NVIDIA Research. Today I'll be talking about our work on multimodal unsupervised image-to-image translation. So I'll begin with this movie. This is an example outputs from our algorithm. The task is to convert dog to cat. And because we do multimodal, we can, for every input dog image, we can sample a distribution of variety outputs and make all of them do the same ear moving action as the input dog. So I've been working on this problem for some time. Earlier, I was working on the coupled generative adversarial network, where we try to learn a joint distribution by using samples from the marginal distributions. And later, we intended to unsupervised image-to-image translation, basically build a link between input domain A images to a corresponding output domain B image. And this is my latest work on this domain. We tend the previous work, which was limited to unimodal, one-to-one mapping, to multimodal, one-to-many mappings, a dog to many cats. And these are my co-authors. I sent them for for the support. Yeah. So I'll start with the introduction. The problem is image-to-image translation. So generally, you have an input image in one domain. You want to learn a function f that's map the image to a corresponding map the input image to a corresponding output image in another domain. The example here is Sunny to Rainy translation. So this problem has many applications, including converting semantic label map to image, day to night translation, the winter to summer. And you can also use this technique to create artistic effects for your video game. Also from sketch to images. And there are many other applications. All the results you see here is produced by GAN-like algorithms. So the image-to-image translation problem has been studied in different settings. I like to call them like a supervised versus unsupervised. Of course, you can also call it paired versus unpaired. So in the supervised setting, you have a training data set for every input images. For every input image, you have a corresponding output image. And your goal is to train a function f that can learn the mapping from input to output. So you basically do the data fitting. In the unsupervised setting, you don't have corresponding images. All you have are two data sets, one from each domain. A data set of image in the daytime domain and a data set of image in the nighttime domain. And you want to learn the translation unsupervisedly. In terms of the mapping function, we can also divide the image-to-image translation into unimodal and multimodal. For the unimodal setting, you actually model the conditional distribution as a delta function. For every input images, you only have one output image. Give a dog, you output a cat. In the multimodal setting, you model the conditional distribution as a distribution, non-degenerated one. For input dog images, you can generate varieties of output cat images. Through this slide, I try to categorize several existing works into different categories based on supervised, unsupervised, or unimodal, multimodal. The pics-to-pics work presented earlier by Phil belong to supervised unimodal, one of the very first work on image-to-image translation. And of course, we also have CRN work, super resolution GAN. For the unsupervised, there are many works, including my unit, disco GAN, cycle GAN, dual GAN, domain transfer network, star GAN. For multimodal supervised setting, there's P2P HD and bicycle GAN. And the topic of today is unsupervised and multimodal. There's a unit, and there's a recent work called augmented cycle GAN. I just want to use this slide to quickly refresh the idea of GAN. So basically, you have an input random variable z, and your goal is to train a generator that can convert z to an output image. And you also have a discriminator whose job is differentiate is the image coming from the generator or one coming from the real image. And by setting up a zero-sum GAN played by the generator and discriminator, and by using the alternating gradient update step, eventually the distribution of the fake images will approximate the distribution of real image. For the image-to-image translation, we are actually operating in the conditional GAN setting. So the input is no longer a random variable, it's an image. And in this case, you want to convert a data image to a nighttime image. The generator tries to synthesize a nighttime image for every input data image. And your discriminator is to differentiate is a real nighttime image from the dataset or one synthesized from the generator. Of course, you can do the reverse order. For a nighttime image, you want to train a generator to synthesize the data image. I mean, by image-to-image translation, we hope the translated output images correspond to the input images. The location of the cars should not change, and where the buildings are should remain the same. However, by applying the alternating gradient update, all you have is the following property. The conditional distribution of your output images, which is in the first case should be the data image, will the output nighttime image will approximate the distribution of real nighttime images. And similarly, for the following, the output data image from generator 2 will approximate the real data images. But we don't have the desired property that the conditional distribution will match the real conditional distribution. What do I mean is, through GAN training, the output from the generator 1 can be a rigid nighttime image, but it may not correspond to a real translation of the input. You can see an image, a very good nighttime image, but the location of the cars may be different to the input image. So it means that we need something more to put into our learning in order to get corresponding output images for this image-to-image translation task. So one of the most powerful constraints is the cycle consistency constraint. I think in the morning, Taesung gave a great talk on this topic. So the idea is you have two spaces. X1 is the domain A images, X2 domain B images. Cycle consistency said that if you learn a function G1 that can map domain A to domain B and a function G2 that can map domain B to domain A, then when you apply them sequentially, you should be able to come back to your original location. So it's pretty much said that when you apply these generation functions, recursively, you'll go back to yourself. So, but for image-to-image translation, what we want is the conditional distribution. Given the input and the corresponding output nighttime image should match the real one. So, I would like to say that actually, if we have the conditional distribution matching, then we will have the cycle consistency matching. So cycle consistency is a necessary condition for the conditional distribution matching to happen, but not the other way around. So it tells us there's maybe something more we can do beyond cycle consistency, because it's necessary but not sufficient. I will use the following examples to illustrate. So we have X1, X2, two image domains. In S1, you have two hearts and two triangles. And X2 is supposed to be another domain where it's upside down. And the color also change a little bit. So here I repeat the domains twice and show how what does the cycle consistency mean. It means, for the orange heart, after applying the generation function recursively, you will go back to the heart. And similarly, for the other X2 domain, you will have the same property. But however, if you mess up the generation function, for example, here you have the red heart, you go to the purple triangle, but it's, the G2 can still map its back to the red heart. Under this scenario, you still have the cycle consistency. So what do I mean is there are many solutions the cycle consistency are satisfied. And not all of them are good image translation. Not all of them give you good image translation results. But I mean, this is the nature of the problem. So for this problem, we only give samples from marginal distributions, but we want to estimate the joint distribution. This is impossible in theory. So here, I try to introduce our shared latent space. Try to. Okay. Should I open again? Okay, so what should how do I copy this one? Copy this one. This one. Oh, it's bad. Go to the sorry. Okay.
Yeah, cool.
Okay. So here I'll be introducing our shared latent space. So this is the idea. So in the top you see the cyclogen. You have two image space. So in the with the shared latent space assumption, you assume there's a shared latent space between these two image domains. And then you have the following. Instead of have two functions, G1 and G2, you now have four functions. Encoding function E1 encode an image in X1 to the latent code, and also an encoder function E2 from the other domain to the latent code. And you also have two generation function from the latent code to the first domain and the latent code from the second domain. So the idea is actually motivated by a classical idea from machine learning. Data live in a manifold, and we assume that domain A images has one manifold, and domain 2 images also have one manifold. Through this shared latent space, we want to align them together. So it's additional constraint to the cycle consistency constraint. And in the test time, you compose the E1 and G2 for translating image from the first domain to the second, and similarly E2, G1 for the other way. I will not go into the detail because it's not of my focus today, but I will just show some results we achieved by applying such constraints. Yeah, so this task is for day to night translation. It's done in the unsupervised setting. For every input daytime image, we have output nighttime image. You can see that our result the result is quite good, but they still contain a lot of artifacts. But you can basically see we kind of can to large extent make it then look really like nighttime images. So here's another example where we translate wintertime image to summertime images. You can see that we remove the snow, replace snow with grass, and add tree leaves back to the trees. And here's example of sunny day to rainy day translation. You can see that the output kind of simulates that water on the road surfaces and make the blue sky kind of cloudy. So for the multimodal supervised image-to-image translation, we actually extend the shared latent space idea to partially share the latent space. So what do we mean is, in the unit model, we have one shared latent space, which is Z. In the Multimodal, the multimodal one, we actually decompose the shared latent space Z into two parts, the content and style. The content is shared by two domains, but the styles are not. So you can think the content is more like the pose or some geometry information, and the style is more like the texture or some kind of domain-specific information. So, when we have an input image from the first domain, say here is a leopard, we extract a content code and the style code. Once we extract the style code, we just throw the style code away, and now sample different style codes from the style domain of the domain 2 images. And for each different style code from the domain 2, combined with the content code extracted from the first domain, we can synthesize different translation of cats. And S2 here is actually a sampleable space. It's actually a Gaussian space in our case. So you can just sample a distribution of different output cats. And so why do we want to do multimodal? I would argue that image translation is multimodal in nature. For input data image, there are many different nighttime images that can correspond to the one data image. So we hope that by incorporating this nature into our modeling, we can improve. One is the diversity of the output, the other is the visual quality of the output. So I will now dig in the details of our model. So here we have X1, which is an image from the first domain, and we extract a content code C1 and a style code S1, and we combine them to reconstruct our input image S1 hat. We do the same thing for input domain 2 image, S2 to S2, C2, and reconstruct X2. We call this within domain reconstruction stream. During training, we also have the cross-domain translation stream. So basically, for input X1, we extract the content code and randomly sample some style code from the style domain 2, and have X1 to 2, the translation from domain 1 to 2. We do the same thing for X2, have S2 to 1. Now, we also reconstruct the latent code. So we reconstruct the C1, which is used to control these images, also the S2 reconstruct this image. Okay. Now we use something called bidirectional reconstruction loss. Okay. So it's bidirectional in the sense that we not only reconstruct images, we also reconstruct the latent codes. So basically, for the input and reconstruction, we minimize these loss, their difference. And for each content code and style code combined to generate the translated images, we want the extracted content code resemble the original input, and similarly the original the output style code, the extracted style code, resemble the input style code. Of course, we also have the GAN loss. We want the S2 to 1, the translation from domain 2 to 1, resemble images in domain 1. And similarly, for S1 to 2, we want it to resemble image in domain 2. We use a special network architecture. We call it ADA-in autoencoder. So basically, for input image, we have a kind of two encoder. One is the content encoder, which is basically some convolution operation and followed by several residual blocks. And we also have a style encoder to extract the style, and similarly followed by some convolution operation and global pooling and fully connected layer to extract some style code. So the decoder works as follows. So it has residual blocks, but we use a normalization scheme called ADA-in. So basically, we perform instant normalization for the residual activation within the residual blocks. But after normalize the activation, we provide a new mean and deviation coming from the style encoder. So this is based on the observation that's in the ADA-in paper published by Xun in last year's ICCB. Through control the mean and variance, we can generate image of different styles. So now the style encoder extracts this latent code and then generates a bunch of mean and variance to put into the residual blocks, and eventually followed by several upsampling convolutions, and we can generate reconstruct images. And for domain transfer string, the input is from domain A. The style code is randomly sampled, and you will generate through this decoder. We can generate an output image in the other domain. So now I'll be showing some results. So here we show the sketch to image translation. This data set is given in the supervised setting. For each input, you know the output. But in our training, we do not use this correspondence. We just use them as they are coming from two different data sets. And now for the input, by applying a trained Multimodal, we can generate different output, different shoes with different colors, different styles, and we can also do the same for the sketches. So we will have a different amount of textures, edges from the textures. And you can also find result here for the sketch to handbags, different color, different styles. So here's some examples for animal translation. So the input is cat, and we can synthesize different big cats, tiger, lion, and leopard. And here is for cat to dog translation, different breed, and other examples. So you can see that the translation output pretty much keep the same pose as the input images, but different domain is still some kind of difference. For big cats, the distance between the eyes and the mouth is usually longer than house cats. So when you do the translation, you will see the location of eyes move. So this is kind of it's beyond style transfer, beyond changing the textures of the input image. You also to change the geometry a bit. There are also failure examples here. You see, for these input leopard images, we actually translate it to a husky with the tongue coming out. This is due to in our data set, many husky like to have their tongue out, so kind of bias coming from the data set. So here we show some result between synthetic domain and real domain. Here we have input image from the cityscape, and the output, the model is trained on Cynthia and the cityscape, and in Cynthia datasets, they have different weather conditions. So now for the same input, we can synthesize different synthetic images with different weather conditions, heavy rain, snow, or sunset. And for the same input synthetic images, we can synthesize different output real images, and these output images differ in their raw textures. And here's another examples. For the summer to winter translation, with the multimodal, we can now sample different amounts of snow. So the left image has more snow, and from left to right, the amount of snow accumulation reduces. And here is a winter to summer translation, and we can generate summer images with different amounts of tree leaves, and which was not possible in previous model, which do the unimodal, which learn a unimodal image-to-image translation function. So, we can also achieve HD image translation results. The image here you see is at least 2K resolution. So we have here is from Yosemite summer to winter. We can synthesize different different winter images, different time of the day, and similarly for the winter to summer, we can also generate different amounts of the greenness and different time of the day. So I will skip the evaluation for now. There's one more example where with this model we can do example guided image-to-image translation. So instead of rendering sample a style code, we can extract the style code from input style images. So for example, we want this leopard to have to translate this leopard to a cat, and not just any cat, but it's a cat with this with the texture provided by the style image. And here are more example, more results for this input shoe sketch. By providing different style images, we can generate different output shoe images. And similarly for this input big cat, we can generate different output house cat. I will also skip this comparison. So to conclude my talk, so I kind of give an overview of the shear latent space assumption and their use for the image-to-image translation problem. And we talk about our multimodal unsupervised image-to-image translation algorithm, the MUNIT, and the example guided image-to-image translation. And the code is available here, and I'm ready to take questions.
Thank you, Mingyu.
Thank you.
This is very slow. Try yours first.
It's my great pleasure to introduce Julie Hoffman. Julie is a postdoc researcher at UC Berkeley, working with Alyosha Efros and Trevor Darrow. She obtained her PhD from Berkeley as well, advised by Trevor Darrow. Her research focuses on transferable representation learning for visual recognition, such as domain adaptation and lifelong learning. So she will join the Georgia Tech as an assistant professor, I guess, next year. Let's welcome Julie.
Hi, everyone. So today I'm going to be talking about domain adaptation, and because it's the GAN workshop, of course, it's going to be adversarial domain adaptation. So in general, when we're talking about a problem like domain adaptation, just to make sure everyone is on the same page, the goal here is to be able to eventually recognize things in an environment where you have very little access to labeled data. So this is really in contrast to the common paradigm that you might see in standard visual recognition. So here, normally what you're confronted with is a supervised learning procedure where you have access to these huge data sets. So here I'm showing a depiction of performance on this ImageNet test set over time for classification. And as probably all of you know, performance just went up and up and up in the last few years as people developed bigger models, had more compute, and really got to utilize these millions of images in order to train this model effectively. But this plot is a little bit deceptive because it's really still monitoring progress on a held-out test set that's drawn from the same distribution as the training set. And this makes sense. It's a standard machine learning paradigm. But unfortunately, it doesn't always match what you see at test time. So to illustrate this, we can look at a small example. We can take one of these big ResNet models, and it was doing very, very well at recognizing these 1,000 categories. But then when we try to recognize the dog in this video, what we find is that that same model can no longer recognize the salient object. And this is something that you can perceive in many other contexts as well. But in the case of this dog example, what we're finding is that really we're encountering a problem with what's called dataset bias. And what that is in this particular case is that ImageNet, even though it's millions of images large, still has a very inherent bias to all of the images that are represented. And that bias is precisely a capture bias and a still image bias. So if you think about how this data set was collected, it was collected by scraping social media sharing sites. Now, when you're trying to share images with your family and friends, you have a particular bias in terms of the type of images that you would like to share. So in particular, if you're taking a photo of your dog, you're probably very likely to post a photo of the dog's face. This makes sense because that's what seems interesting to you. You're also very likely to take a couple of photos and choose the one that looks most visually appealing to upload. And that means that these sort of images are, in general, higher resolution, have nice lighting conditions, and probably have proper composition in the sense that the salient object is in the center of the frame. But now, move to a YouTube video, and you have a completely different set of bias. So here, you're trying to show an interesting action. And so when you look at the still frames of this video, you realize that you now encounter things like lower resolution, motion blur, and a wider variety of poses than might have been apparent in the still image database. So in this talk, I'm going to show how we can use adversarial learning procedures in order to help us to generalize models that were trained under a supervised paradigm for use in a new setting where you may not have access to lots and lots of labels. And this problem has been classically studied under the notion of domain adaptation. So in domain adaptation, you have access to a large labeled data set that we'll call the source data set. This might be the ImageNet data set, or it might be a collection of images taken from a product warehouse where the labels are easy to acquire. Or it might be simulated imagery where the labels are implicit. In all of these cases, the key is that we have access to a lot of labels and can train a strong supervised learning model. But at the test time, we want to recognize things in a different domain. In other words, a different collection of images that's drawn from a different set or different distribution. So it could be this still images to the video database. It could be trying to recognize those products as they appear in the wild. Or it could be trying to train in simulation and make sure that it actually performs well in the real world. But no matter which scenario you're considering, we're always trying to reuse the information that was acquired in the standard supervised learning paradigm on your source data, and then generalize it or adapt it for use in the target setting without asking for lots of human intervention. So the classic setup for adaptation, if you were talking about it 5-6 years ago, would be that you had access to a large labeled source data set, shown here by the product image, and then you had your unlabeled data set, maybe the way the product looked as in the wild. And you would define some sort of function or a representation that could be used to extract the relevant information from the image, represented in some vectorized form, and importantly, that feature could then be used for training your supervised model, maybe recognizing the bottles and mugs in this case. And the problem that we encountered over and over again was that in this fixed feature representation, you would find that there was a distributional mismatch between the collection of source and the collection of target images. So the idea that I'm going to talk about today, and the idea that you've probably heard a few other times either today or throughout this conference, I've seen many other works also taking a similar type of approach, is to think about the problem here as really being one of having an not as useful feature space as you would like. And in particular, if you have bias in your original source and target data, maybe that's okay. And maybe what we should seek instead is to find a feature representation which ignores those differences and only pays attention to the salient information that's useful for semantics. And so to do that, we're going to replace our fixed features with end-to-end learned models. And to supervise the learning of those end-to-end models without having access to any target labels, we're going to use this distribution discrepancy notion as a way in order to inform the updates of the representation. So we're going to explicitly minimize the distance between source and target, and this will provide us with a more domain-invariant feature representation. So some of the earlier works that did this looked at pretty simple statistical alignment techniques. So things like max-mean discrepancy or just simply aligning the means between source and target. Then some later works worked on kernelized versions or on correlation-based alignment methods. Today, as it's the adversarial tutorial, I'm going to talk about aligning based on what's known as the DH discrepancy. And I'm going to go into a little bit of technical detail as to what that is in just a second. But one kind of key piece to note about this is that it has a very nice connection to the theoretical domain adaptation literature, which says that you can upper bound, probabilistically, the error that you expect in your target according to a function of this notion of discrepancy. So discrepancy, as it's written here, is really just a function of how likely is a particular partition of the space under your known source and target distributions. And if you have that notion, or if you have the ability to compute that, well, then you can produce this probabilistic upper bound on what you expect your error to be in your test data. And it's going to be a function of the error that you saw on your source data, which again, we have access to lots of labels in the source, so we can assume that that should be relatively small. Together with this discrepancy, as well as a term that relates to the best possible expected joint model for your source and target. So now that we have that idea of, okay, this gives us some sort of grounding in, based on the theoretical literature, that we might expect that maybe minimizing this discrepancy would result in minimizing the expected upper bound on our error. Well, now we need to be able to actually compute this quantity. And in general, when you're talking about these distributional quantities, if you don't have access to the true distribution, that can be a daunting task. So what we have access to are some samples from the source and some samples from the target. And so really, what we're going to hope for instead is just computing an empirical approximation to this notion of how far apart are my product images versus my real-world images. And just this next kind of couple slides are basically for whoever is interested in this, but so I'll go through it relatively quickly. But essentially what you can do is you can compute this empirical approximation by first looking at 1 minus the probability of one of these two probability guesses, in this case source, being flipped to look at the label being 0. And then examine this quantity and notice that this term will be maximized exactly when both of these probabilities are 0. And it turns out that you can actually compute that based on training a classifier and looking at the classifier error. So this is kind of the key detail that's going to start connecting us up to these adversarial learning procedures. And that's simply that this notion of how far apart is source and target, in terms of this notion of discrepancy, can be empirically approximated by looking at the error of our domain classifier. Now, in this case, a domain classifier is simply how well can this classifier perform at disambiguating in feature space. Did this feature come from my source data set or did it come from my target data set? And sort of intuitively, if you can make that distinction, it means that these points fall in space in such a way that they're well separated. And this means that it's somewhat hard to reuse a classifier from one collection of data for the other. So now that we have this way to actually compute this notion, we can now operationalize the minimization of it. So we're first going to estimate the discrepancy by training a classifier. And then we're going to update the underlying representation space so as to confuse this classifier. And this is where the adversary comes in. So to understand this in a little bit more detail, we can look at a simple example of how this optimization might work in practice. So here I'm showing a collection of your source data. Here it's the product images, together with their labels. And because these are a large labeled corpora, you can use it in order to learn a representation, which is very useful for classifying these object categories. So once you've done that, this data will fall somewhere in space such that an object classifier will perform well at distinguishing between the bottles and the mugs. Now the problem arises when you use this representation in order to view data from your target data set, in this case the real-world images. And in particular, if these two distributions are far apart, or if the discrepancy is large, then the model that you trained on the red data points in order to determine where are the bottles and what are the mugs is less likely to work well on these blue unlabeled data points. So we're going to directly optimize against this happening. And the way that we do that is we start by approximating how far apart they are. And we do this, again, by training the domain classifier. We then are going to update the underlying representation, which really means where do these points fall on the screen as I'm depicting it here. And we're going to update it according to confusing this domain classifier. So once we've done this, the points will move in space in such a way that that classifier no longer correctly distinguishes the difference between the red source points and the blue target points. And now we can use the labeled source data again to train an object classifier under this new representation, and it will perform better on the more aligned source and target data. Now, this procedure is, of course, iterated in high-dimensional space, and you basically keep going until there's no longer a domain classifier that's able to tell the difference between the source and the target data. Now, because this is an adversarial method, as many of you are probably aware, adversarial methods can be notoriously tricky to train. So I want to just take a brief moment to mention one optimization trick for this particular line of work. So if we go back to the math of how we could compute the empirical approximation of this distance, I said that this quantity was maximized when both of these probabilities were equal to 0. But that's not the whole story. They could also be maximized when both of them are equal to 1. And although this may seem like a minor detail, it's actually a pretty important point, because what it says is that the labels that you choose to designate as 0 is source, 1 is target, or 1 is source, 0 is target, is pretty irrelevant. Either way you train it, it's going to have the same outcome. And so what I've found, at least when training these types of works, is that you can use this intuition to help stabilize the learning procedure. And in particular, instead of training a discriminator and just always updating in one direction, you can utilize the fact that the direction or the sign of this classifier is irrelevant. And you can just always optimize your representation according to the best possible discriminator direction. So now that we have all of that together, this is the domain adversarial learning procedure. And as I presented it so far, this is really a technique for creating domain invariant feature representations. And we do that by looking at distributional distances in the representation space. But one could equivalently look at aligning things in the pixel space. And this would match a lot more closely to many of the talks that you've seen today. So in particular, in conditional GANs or in unpaired image-to-image translation, you would see that you had access to 2 collections of data, and you were trying to manipulate the way that images looked from one collection to make them a closer match to the way they looked in the other. Now, all of these sort of completely unsupervised learning techniques differ in some key ways from domain adaptation. In particular, in domain adaptation, our end goal is not to generate a better looking new image. Our end goal is to improve the performance in the target setting. And this means that we have a very explicit task in mind when you're doing image-to-image transfer. So to understand why that can be important and how we can also use that to our advantage to actually produce stronger, more semantically meaningful translations in certain contexts, I'm going to show you a small example on digit adaptation. So here what we have is training on Google Street View house numbers. So there we have lots and lots of labels. And then we'd like to evaluate our performance on recognizing digits in the MNIST data set. So standard conditional GANs would optimize according to a criteria of stylization, or in other words, if you take the source Google Street View image, pass it through your generator, you should be able to produce another image that cannot be distinguished from true MNIST digits. You've seen talks about other ways to improve upon this and prevent some sorts of mode collapse, as well as retain low-level structural consistency by things like cycle constraints. And in this case, you're going to take the first stylized image and then map it back to the source domain and make sure that it is a good reconstruction of the original image. But even with both of those criteria, stylization and a reconstruction objective, you can still run into peculiar results. So for this example of Google Street View to MNIST, I'm just going to show you one type of failure that can happen. So here, I'm showing you some source images from Google Street View house numbers. And these are the images that are generated after stylizing them to look like MNIST. It's good, it's the correct style. And maybe surprisingly, these are the reconstructed images from those MNIST stylized images. Again, they're a pretty good reconstruction of the original image. But of course, if we want to use these intermediate images for domain adaptation, there's a fatal flaw here, which is that these images have flipped semantics. And if we really want to use these middle images in order to train a model that can then be used for recognizing an MNIST, this is a critical error that we need to fix. So to do that, to prevent these types of label flipping that occur, especially in scenarios when the overall image changes dramatically, like this Google Street View to MNIST, what we do is a very simple modification that you might have seen in other works like Pixel DA, which is that we add what's called a semantic consistency term, or semantic consistency objective. And what this is very simple. It's saying, in domain adaptation, we have a task. We know what the task is because we have lots of labels on the source that tell us what the task is. We know that we can use supervised learning to train a model to recognize these digits in Google Street View. And we know that that model doesn't perform as well as we'd like in MNIST, but it performs better than chance. And so we can use this as a signal and measure what is the predicted output before and after we do this image translation. And we can simply ask, hey, don't flip the labels. Make sure that it predicts the same label before and after transfer. And once we do that, we now can take these Google Street View images and we can generate images that retain the proper semantics and start to look like MNIST. Of course, they won't be perfect replicas of MNIST. There'll still be some misalignment with the true digits. And so then we further can combine this with the representation space alignment that I mentioned earlier. And once you do that, you can look at your overall performance at recognizing MNIST digits. So if you just train with Google Street View and then you evaluate an MNIST, you get about 67% accuracy. If you use various forms of feature space or image space alignment on their own, you can improve significantly. And kind of interestingly, if you can combine them together, you get even stronger performance gains. And I probably don't have to tell this audience this, but just for your reference, if you trained on all 60,000 MNIST, you could get near perfect performance. But the important point here is really the fact that without any labels in MNIST, we can use these sort of statistical alignment techniques both at the representation level and at the image level in order to take our performance from 67 up to 90. So in the remaining couple minutes here, I'm going to show you some examples on a larger problem statement. So here, we're going to talk about semantic segmentation in driving scenes. And semantic segmentation is a very popular topic right now, and a lot of people are working on collecting different data sets. But unfortunately, because it's such a detailed annotation, it's extremely expensive to collect these annotations. So in particular, a data set that's being collected at Berkeley, it costs between $10 to $12 per single image. And if you're really trying to tackle self-driving applications, you have to understand that there are all kinds of variations that happen in the world. So you have to be able to capture a data set that has enough variety, that it has all your different weather conditions, is taken on different sensors, on different cars across different cities. And this becomes just overwhelmingly expansive. And so what we're going to see is, can we take whatever data set you have, train the best supervised model you can, and then adapt it for use when a new environmental condition appears at test time? So the first such example we're going to look at is cross-city adaptation. So to study this, we're going to use two different data sets. The first, we're going to assume that we have labels from the cityscapes data set. So this is a collection of images taken from around German cities. Next, we're going to evaluate performance of that model in a new data set that's collected at Berkeley, which has images taken from around the San Francisco area. There's all kinds of small differences between these cities. The size of the roads vary. There's more tunnels in San Francisco. The conditions of the roads look very different. San Francisco is not known for its infrastructure necessarily and has some potholes and other uneven road conditions. So we're going to just look at one simple example here. And this is a test time image taken from this San Francisco driving data set. And I'm going to zoom in on this strange-looking building here, which is made out of concrete. And what we see is that before adaptation, this building is confused with sidewalks and roads. But then after we adapt, we're able to start correctly identifying it as a building. As another example, we can think about adapting across weather conditions. So here, in order to study this, we're going to use the Cynthia driving data set, which is a synthetic data set that renders driving scenes under different weather conditions. And we're going to imagine that our training data came from the fall, and we'd like to evaluate how well does it perform when there's snow on the ground. So the first thing that we can do is we can use these unpaired image-to-image type translation techniques in order to perform pixel-level adaptation. We're going to start with our fall image, and then we're going to make it look more like an image that would have been drawn from the winter distribution. So after we do that, we get this image, and the main differences are simply that snow appears on the sidewalk as well as the rooftops. And then we can evaluate our overall performance on the winter data set. And here I'm showing one such image together with its ground truth. Before adaptation, not surprisingly, there's a whole lot of confusion on the parts of the image that are covered in snow. So in particular, the road is confused with a building. But after you do these adaptation techniques, you start to be able to recognize the road more consistently, as well as a little bit of the sidewalk in this example. And this is something that we saw systematically over the data set. As a final example, I'm going to talk about adapting from simulated to real-world driving imagery. So I mentioned before that driving application has a lot of possible variations that you might encounter. And so, rightfully so, many people are thinking, can we generate all of these examples and then use that within our strong supervised learning frameworks, and then just focus ourselves on learning to adapt between these simulated images to the real-world images. So here we're going to look at adapting from the GTA driving data set, which has fairly realistic renderings. And then we're going to evaluate our performance in the real-world cityscapes German driving data set. So we start with this image from the GTA data set, and we then map it to look more like a cityscapes image. So the main differences to notice, especially because they're particularly salient for our end recognition performance, is that the road in GTA is emulating Los Angeles. Los Angeles, turns out, has similar roads to San Francisco. They have potholes, they're not smooth. But after we adapt an image space, we find that we now have a nice, smooth, gray road. Other small things are things like the center line changes from yellow to white. And in general, one of the kind of fun parts about working with image-to-image translation techniques is you really get a visual cue as to the particular biases of your data set. And in this case, that pops up in the form of a hood ornament. So all of Cityscape's data set is collected on the same car that always has the same hood ornament visible. So after image translation, we now have a hood ornament. So these kind of unpaired image-to-image translation techniques can be very useful in the adaptation setting. And you can really use them in combination with the standard feature alignment techniques that people had been using in adaptation literature in order to produce the best possible joint model. So here's one example from the Cityscapes test set. And what we find here is that before adaptation, there's a whole lot of confusion. And then after adaptation, you're able to start more accurately recognizing the road, as well as other salient features like this pedestrian or small street signs. And this, again, you can find over and over again. You recognize the road more clearly. You find new small objects. And just for reference, I'm going to just explain very, very briefly that there's still a long way to go. You can get strong performance improvements looking at mean IOU by using the combination of these image space and feature space alignment techniques, but you're still not fully approaching the oracle or the supervised learning performance. And I just want to make one final comment about evaluation in general, which is to say that there are many different ways that we could evaluate all of these semantic segmentation models. Mean IOU is just one such metric. But if you just make a small tweak and look instead at something like frequency weighted, which means that you are paying attention to how much real estate does a particular object class occupy in an image, the results look a little bit different. And what this tells us is that, first of all, if what you care about is things like street signs, you better make sure that your metric takes that into account, and you should probably modify your method to make sure that you're weighting those sort of classes heavily. But secondly, it gives us some insight into when you're doing overall statistical alignment techniques, they're always going to be biased by the most prevalent classes. And so if that's not your desired effect, then you need to think up different types of algorithms. So at this point, I'm out of time. So I'm going to stop here and quickly thank my collaborators who put in a lot of effort into making all of this work possible. So thank you.
I think we have time for only one question.
Thanks for the great talk. I'll go to the question quickly. The approach to do the domain adaptation helps in the cases we don't have any data. In real world, we have some data. So weekly supervised learning would help. Any study on like how effective is this with respect to the number of samples we need, things like that?
Yeah, absolutely. So unsupervised adaptation is perhaps just the simplest formalism to think about, but of course in the real world, if you have some labels, use them. And you can improve your performance pretty dramatically by using just a few labeled examples. We have some work from NIPS last year that looked at also task transfer in few-shot learning, and you can basically see these sort of plots that basically tell you how many examples do you need before you start approaching supervised and things like that.
Thank you.